Hi everyone, I hope this video finds you well. Today we're going to be starting into the linear algebra portion of our class. To do that, we're going to be working our way through section 2.1 from your textbook, talking about matrices, just giving some basic definitions and notation. This section is going to feel a bit different than what we were just doing with differential equations. And we're going to be building a lot of this sort of matrix stuff and then eventually into the linear algebra from the ground up. So there's going to be a lot of sort of basic definitions and operations that we need to define. While this will be a bit different, you should keep in mind that linear algebra is very intimately connected with differential equations. Linear algebra is essential for solving higher order differential equations, for talking about systems of differential equations, and for understanding the theory behind solution sets for differential equations. So we'll definitely see how the stuff that we're going to be learning in these next upcoming sections and weeks really does relate back to the differential equations we started with. We'll also spend a little bit of time, though, just talking about some of the applications that directly come from linear algebra, because it is a worthwhile branch to study on its own. However, without sort of further ado, let's just start with some basic definitions. So first of all, what is a matrix? Well, matrix is just simply a collection of mathematical objects organized in sort of a row-column format. So basically, it's a bunch of mathematical objects organized into a rectangular format. You'll notice that we're calling attention to usually having real numbers as those mathematical objects. That's going to be the case for our class, unless we specifically say otherwise. However, you should keep in mind that matrices can be more general. You can have the objects be complex numbers, they could be functions, they could even, in theory, be matrices themselves. So you could have a matrix of matrices. However, if we don't say otherwise, we're going to make the sort of generalized assumption that we're going to be dealing with real numbers. Those objects, those mathematical objects inside of a matrix, each one of those as an individual is what we call an element. So an element is just our name for those individual objects that make up the matrix. When we're discussing a matrix, we also often talk about its size. We're going to use the notation for size as m times n or m by n. The convention there is that m is always going to denote the number of rows, whereas that n is always going to denote the number of columns. So we're always reading the size of a matrix as rows by columns. Now, of course, that multiplication sign is there for a reason. If you multiply the number of rows with the number of columns, you do indeed get the number of elements overall. So it's not just that we want to use a multiplication sign there as notation, it also is the sort of notation that makes sense. M and n together make up the size of a matrix, but individually, m and n are often called the dimensions of the matrix. You guys have encountered dimensions before, like R2 is dimension 2, R3 is dimension 3. Later on in our class, when we're talking about vector spaces, we'll talk more generally about dimension, and we will see that the choice of the word dimensions for these numbers that relate to the size of the matrix really do connect with dimension in general for dimensions of spaces, etc. So it's a worthwhile term here to have. A couple of special matrices that we should be aware of is if we have something that is 1 by n, meaning a single row and a bunch of columns, we call that a row vector. Whereas something that has a bunch of rows but a single column, so m by 1, that special type of matrix is often called a column vector. Furthermore, a matrix whose number of rows is equal to its number of columns, so n by n, is called a square matrix. That should make sense because visually, if you have the same number of rows as columns, when you put that into a rectangular format, it will appear as a square. Let's talk a little bit about sort of some of the mathematical notation that we should expect here. So a little notation here. So let A be a matrix. Well, then if we write something like A sub ij, this equals the element of A in row I, column j. So when we write A sub ij with those two subscripts, we're talking about a particular element from that matrix. And just as normal, we read that as the element that is in the ith row with the jth column. Sometimes you'll see the notation alternately. We will sometimes use Aij like that. Some people like that notation because then the capital letter indicates that you're talking about a matrix, whereas the lowercase letter talks about a single scalar, a single element of that matrix. Of course, with the subscript, as soon as you see I sub j, you know you're talking about an element, so it's not really necessary to shift between upper and lowercase, but sometimes you will see that, especially if you go online and look at other sort of resources that are out there. Let's also talk about what it means for matrices to be equal. Right? It should be pretty clear, but we do need another quick statement here. So, definition, two matrices A, B are said to be equal if, well, one, A, B have same size. So the two matrices have to be identically sized. And two, A sub ij equals B sub ij for all, let's say, 1 less than I less than M, and 1 less than J less than N. So basically this is saying that all of the elements have to be identical and the two matrices have to be the same size. That should make sense, but do keep in mind, right, it is a little bit different than just saying the numbers are equal. The elements all have to be the same, they have to be in the same positions, and there have to be the same amount of elements for two matrices to truly be equal. All right, let's get a little bit more practice with some of this sort of terminology about a row and column and the elements and everything with our next sort of example. So, as an example here, let's let matrix A be the matrix 1, 3, 2, 4, 5, 0. And let's let B be the matrix 2, 0, 1, negative 1, 3, 5, negative 5, 1/2, 8. Okay. And let's just determine a couple things with this. Let's just determine, how about do A12, and let's determine B23, and let's also determine B33. So let's just do those real quick. So if we're looking for A12, we're sort of reading that as the first row, second column. So we'd be looking at that value right there in the first row, second column. So that would tell us A12 is just equal to 3. If we're talking about B23, would be in the second row, third column. So we'd be looking there at 5. That tells us B23 is equal to 5. And then B33, right? Well, if we look for that, that would be third row, third column. That would be right there. And that value would be 8, right? So each of those are elements of these different matrices. As you can sort of imagine, right, as these sort of rectangular matrices here, we should also just maybe make a note in general, right? Let's just note here, A is 3 by 2, 3 rows, 2 columns, and B is 3 by 3, and B would also be considered squared, just to get full use of all the terminology that we've introduced thus far. Okay, so let's also talk about how you can decompose matrices into rows and columns, right? So if we sort of make a note here, so let's continue this example, right? If we notice, right, we can sort of decompose A into column vectors, right? So we can notice that like A1 would be 1, 2, 5, and then A2 would be that second sort of column, 3, 4, 0. And then notice that we could say A, instead of writing out all that notation, is just A1, A2. Now in your book, you'll notice that whenever they talk about vectors, they recommend like bolding the A1 and A2 to indicate those are vectors. That's hard to do, obviously, when you're writing by hand. One thing you should keep in mind, though, is that a single subscript, right, the fact that we only wrote A sub 1 or A sub 2, sort of indicates that we're discussing a vector there. Whereas no subscript sort of indicates that we're talking about a matrix, and a double subscript, like we had back up here, indicates an element. Obviously, we don't have to decompose into row vectors, so we could, into column vectors, we could also do row vectors. So let's decompose B into row vectors, right? So B1 then would be viewed as 2, 0, 1. B2 would be viewed as negative 1, 3, 5. And B3 would be negative 5, 1/2, and 8. Right? Then we could actually view B as B1, B2, and B3 like that. So all we're saying here is that you can think about the matrices as a collection of elements. You could also think about a matrix as a collection of column vectors like we did in this section here. Or you could think about a matrix as a collection of row vectors like we did here. And it'll be useful in different situations to think about matrices in different ways. So you should be comfortable moving through these different sorts of notation here. All right, let's continue on then and talk about some operations for matrices. Now, eventually we'll be able to talk about dealing with addition, subtraction, multiplication, all your sort of standard arithmetic operations. But we're going to start with an operation that is defined only for matrices, rather than focusing on ones that you guys have seen for numbers or functions previously. So let's go ahead and talk about this definition. So definition. The transpose of a matrix A that is m by n is the n by m matrix with rows and columns interchanged. The transpose of A is written as A with a capital T, so sort of almost like an exponent, but of course it's an operation here. Now, what do we mean by rows and columns interchanged? Well, we literally mean that the rows of matrix A become the columns of the transpose, and the columns of the original matrix A become the rows of the transpose. We can actually write this out in notation. We can say that in A transpose, the ijth element is actually the ji element of the original matrix. So let's do a quick example looking at how the transpose sort of works. So let's let A be the matrix 2, 0, minus 1, 3, 4, 6. And let's have B be the matrix 1, 2, 0, negative 3, 5, 8, 0, 1, 2. Now we can just sort of note here, right, that A is 3 by 2 and B is a 3 by 3 square matrix. So let's determine, we don't really need multiple parts to this thing, so let's just get rid of that. That seems sort of nonsensy. All right, let's determine A transpose and B transpose. So what is A transpose going to look like? Well, what we're going to do is we're going to take each of these rows and view them as columns. So when we do this, right, that 2, 0 as a row is now going to become the column 2, 0. The row minus 1, 3 is going to become the column minus 1, 3, and the third row 4, 6 is going to become the third column 4, 6. You'll notice that A transpose now is 2 by 3, as predicted by the definition. You can also notice that if we look at an element, say A1, 2, so first row, second column of the original matrix, that would be 0, whereas A transpose 2, 1, well, second row, first column, that's also 0. These are going to be the same. And again, that's just understanding the definition of the transpose. Let's look at B transpose. Now, because B was originally square, B transpose is also going to be square, so the size isn't going to change, but the matrix itself is. So this first row here, 1, 2, 0, that's going to become the first column, 1, 2, 0. The second row there, minus 3, 5, 8, is going to become the second column, minus 3, 5, 8. And then finally that third row, 0, 1, 2, is now going to become the third column, 0, 1, 2. That guy, of course, is again 3 by 3. If we look at one of those particular elements, let's look back at B23. So that's the second row, third column here at 8. We can check that that guy was 8. And if we look at B32 of the transpose, well, B32 would be third row, second column. Yep, indeed, that is 8. And those are the same, right? And that shows you how we are doing that element by element. So the transpose is a really important operation because it's an operation unique to matrices. It only makes sense to talk about the transpose when you have a matrix because you're talking about interchanging rows and columns. All right, now we're going to go ahead and give some special matrices, some definitions of some special matrices. Some of these are actually going to relate to the transpose, but all of the definitions we're about to talk about are going to sort of relate directly to square matrices for a while. Now, our focus is not going to be on square matrices only, but for the next few definitions, everything is going to be a square matrix. So let's go ahead and take a look at those.